I wanted to revisit one of the problems from the warm-up just because it may have caused a little bit of confusion. So, and we'll of course talk about this a little bit more today, the squeeze theorem. So, so what actually is the point of the squeeze theorem? Right? What's the idea behind the squeeze theorem? Yeah. The same thing. Got to be also the same thing, right? So if you've got, all right, so what is today, the 2nd? Yeah, it is kind of hard to express, right? Okay, so the squeeze theorem, right, is if you have 3 functions that are in order like that, and you know that f and h both go to the same place as x goes to something, then what, pray tell, would g go to? Probably that same thing, right? So if this, excuse me, and if the limit as x goes to some number of f equals the limit as x goes to some number of h, then the limit as x goes to some number of g is the same thing. So let's call that number L for limit. Then that one goes there too, okay? Now, how we use the squeeze theorem, and this is where it can get a little tricky, is oftentimes you only have one function, right? And so you have g. You got to figure out what f and h are going to be in order to do it, or in order to apply the squeeze theorem. All right, so what was the function, the example in the warm-up video? Not the problem from it, but the example. Yeah. Yeah, the squeeze theorem problem. Mm-hmm. Right. Okay, so let me just call it g of x equals x squared sine of 1 over x. Okay. Now, this isn't 100% true, but oftentimes squeeze theorem problems involve a sine or a cosine, simply because those, like, problems involving those are where the squeeze theorem needs to come up in the first place. So it's kind of, some of these may seem a little contrived. But let's remember a couple of things. First off, what's true about the function sine and also cosine while we're at it? What can you say about the output values from those? So no matter what you plug into sine or cosine, what do you get? I'm sorry? Well, okay, you plug an angle in and you get out a number, which is ratio, right? So the angle part is not there anymore, right? But what are the range of values that you get out of these functions? Like, think about the graph. What are the y values of? Yeah, -1 to 1. Okay, so the output of these things are always between -1 and 1, or of the sine or cosine. Okay, and so we know that this is true. Okay, that sine is between -1 and 1, no matter what's on the inside. Okay, now, yes, there's a problem if x equals 0, but uh, barring that, we're cool. Okay, good. All right, so that said, we can't apply the squeeze theorem yet, because what else do we need? We need the limit of the first and the last function to be the same thing. Well, right now, what are the limits of our first and our last function? One is -1 and the other is 1. Well, those aren't the same thing, right? So the squeeze theorem doesn't help us yet. So what we need to do, well, and for that matter, is the function in the middle the same as what we started with? No. Okay, so we're not there yet. All right, so what was the trick here? How do we turn the middle thing into what we wanted? Multiply everybody by x squared, right? Okay, so if this is true, then this is true. Okay, now how do I know that that inequality, I haven't like messed something up in the process? Right, so what's the danger when you start multiplying or dividing where there's an inequality involved? Yeah, it might have to flip the type of inequality, but under what conditions do you have to do that? If you multiply or divide by a negative quantity. I just multiplied by something. Is that ever a negative quantity? Why not? Okay, that's not quite what I mean. I multiplied by x squared. Is it possible that x squared itself could ever be negative? Why not? It's something squared, right? Something squared can be 0 possibly, but never negative because we are excluding imaginary numbers. Okay, so that, okay? Okay, so that means that we don't have to flip any inequalities and nothing kind of crazy is going to happen there. Okay, now, do we know anything about the limit of x squared and minus x squared as we approach, say, 0 here? What are both of those? They're both 0, right? And so what do we conclude that this limit is? Right. For the same reason. Okay, the squeeze theorem. Okay, so that was the example. But what was the exercise? It looked a little bit different. Okay, so let me pause for a second. Any questions on this before we move on? And am I writing, is my writing, I know it's terrible, but is it at least sufficiently legible that I'm not writing in Greek? That can be arranged, by the way. Okay, good. All right, so the other problem, and I'm going to have to switch to a new page. So anybody need me to stay on this sheet for a second, or are we good? Good? Okay. So the other problem was we had the function g equal to sine squared of x times cosine of 1 over x. Okay, so thinking about this in terms of the previous one, well, where do you think we're going to start with this? What's true about the cosine term? Yeah, so, oops, what? So, okay, the range of the cosine function, yeah, is between -1 and 1. Yeah. Oh, it was sine of x squared. Okay, sorry. Yeah, thanks. That will matter. Are you sure? I thought it was. Um, well, it'll end up working the same way. But okay, so it was this. Well, slightly the same way because sine of x squared. Um, Around 0, which is of course the point that we're interested in, it'll end up working out the same. But yeah, and I'll graph it and sort of show you why. Okay, so we already know this part, and then so what's the guess that we need to multiply everybody by? Sine squared of x, right? Okay, now, is sine squared of x always positive, or maybe equal to 0? I'll take yes. It's something squared, right? So no matter what sine is, if you square that quantity, are you going to get a negative number? Nope. Okay, so we know that this holds. Oops. Okay, now, if it had been sine of x squared, that inequality would hold for a small interval around 0, but not everywhere. Now, that's okay, because what do we really care about? We care about what's happening close to 0. And I'll show you the graph in a minute to sort of flesh that out. Okay. Now, do we know what the limit of the thing of sine squared and minus sine squared are? They're a little more complicated than what we had before, but what's true about those graphs? You guys remember how they look? Yeah, so the sine graph looks like, the wavy thing. If you square it, it's going to kind of look like this, right? But in particular, what is sine of 0 degrees or radians? It's 0, okay? So what are the limits on the outside two guys going to be? They're both going to be the same, and they're both going to be 0, okay? So limit as x goes to 0 of sine squared of x and minus sine squared of x are both going to equal 0. Okay. Now, like I said, I'll graph this in a second, and then I think you guys will kind of be convinced in a different way why this is true. Okay, so what's the limit that we were after? Then the limit that we really cared about must also equal 0. Okay, is that all right? Yeah. Okay, so let's graph this, and I'll show you with Desmos, or yeah, well, we'll just use Desmos. That's fine. And sort of a way you can graphically think about what's happening. Okay, good. All right. So I need Safari. I need Desmos. Okay, so I'm going to graph three functions. I'm going to graph sine squared of x and its negative, okay, because we were interested in those. All right, so we need negative sine, well, I need a parenthesis, then a sine of x, and then two parentheses, and then I need to square it. Okay, so there's that function. And then I also need sine of x squared. Okay, so we got those two guys. And then I also need, well, I'll put the function in question here in just a minute. But if I zoom in here around 0, what do we notice about both of them? So the red one is the negative sine squared, the left-hand piece. The blue one is the top one, okay? So what do we notice? They both go to 0 as x goes to 0? Yeah, okay, so that's good. And then the function in question was sine of x squared times the cosine of 1 over x. Okay, good. And so notice what's true about so that one's the green curve, and you see how it's sort of bounded on either end by the blue and the red curves, and sometimes they happen to intersect, but they never, the green one never goes outside the envelope sort of defined by the blue and the red one. And so if I sort of zoom in a little bit, right, what we see is, well, it kind of gets squeezed in there in the middle, right? That kind of makes sense then, right? Yeah. So, I mean, this is one of those theorems, like we call it the Squeeze Theorem, right? That um, people like Dr. Brown would be like, oh, you stuffy mathematicians, this is obvious to anybody with a brain, and you guys have to make it a theorem and make a big deal about it, whereas the rest of the world just moves on with life. But that's, physicist for you. So, has anybody had Dr. Brown for a class yet? Yeah? No? No? Okay. Well, maybe someday you'll get that honor. Okay. So does that kind of make sense? Yeah. Okay. So the thing you got to suss out here. Oh, and to your point, let me go back and change it where the square is. Okay. You got to suss out what the small function and the big function are. Now, like I said, often these things are trig functions, and so it's not like you're not having to pull it out of thin air. Okay, so let me change this and suppose that instead of the x squared be or the square being outside, it was inside. And let me fix these guys because it's complaining. Okay, so I'm going to put the square here and here and there instead. Okay, it still ends up getting squeezed, okay, but if we look broader, further out, you'll notice that the blue and the red ones sort of switch roles as to who's on top, who's the top bound and who's the lower bound, right? So if we go out to like 1 point whatever, right, you see the blue and the red one are sort of switching roles, okay? And that's because if we square the x before we take the value of the function, it's not true that sine of all positive quantities is a positive quantity, right? So if we take x, we square it, we get some positive number. Take sine of that. Is that number always guaranteed to be positive? No. Okay. And so what happens is that on certain intervals, our inequalities flip. Okay. Now, do we really care what's going on like way the heck out there? No, because what were we interested in with this function? We were interested in its behavior at 0, right? So is it true that the blue and the red one, the two functions are on top and bottom in a region around 0, containing 0? Yes, and that's actually enough for the squeeze theorem. Okay. So in this case, it didn't end up mattering. You were going to get the same thing, even though, strictly speaking, these were different functions. Okay, so does that kind of make sense? Um, and the reason is because -0 and 0 are the same thing, right? Is essentially what it boiled down to. So, yeah. Okay, good. All right, so let's go back to the other stuff for today. And there's a couple of special sort of analytic limits that we want to do. Basically, we want to think about under what circumstances are you just allowed to plug in. Okay, so let me go back to the notepad here. Okay, so so there was one of them on the homework that basically asked something like this. Okay, which is almost so stupid it's hard. What is the limit as x goes to 7 of x? I'll take 7 for, well, how about 7 points, right? What the hell else would it be, right? Okay, so in general, right, the limit law that we used here is that the limit as x goes to something of x is just that something. Now, similarly, why is this true? Okay, so if I take the limit of a constant, why do I always get the constant? I mean, other than like, yeah, this is obvious. Well, how would we think about this graphically? What does a graph of a constant function look like? It's a straight line that is horizontal, right? And the limit is asking a question about the y values, right? As x goes to something, what are the y values getting close to? Well, if it's a horizontal straight line, what are all the y values? The same thing. So what do you think we're going to get here, no matter what x value we're looking at? the same thing, namely that constant. Okay. All right. Now, we have those two results, that the limit of x is just whatever you're approaching, and the limit of a constant is itself. So if I have a polynomial, okay, so what does a polynomial look like? It'd be something like p of x equals, well, what's an example of a polynomial? Just pick one. X squared, right? And you could doctor it up and add other terms, okay? But what is a polynomial in general? It'd be something like this. Right? So it's just a bunch of x to the whatevers, maybe with some numbers out front, and a bunch of these things added together, right? And it's possible, of course, that a bunch of these coefficients are zero. They don't have to appear. And so what are the coefficients in the way that I wrote this here? Huh? The coefficients are a sub something, okay? So what's the biggest coefficient? Or sorry, the coefficient of the largest power? A sub n, okay? What's the least powered coefficient? A sub 0. That's the constant term. And sometimes, just get used to it, I will say that as A naught, N-A-U-G-H-T. That's kind of a British thing that for some reason is stuck in math class. Okay. Yeah, is that okay? Okay, so what's the degree of this polynomial? You guys remember the definition of degree? It's n, whatever n is in this case. Okay, so what do we know about how we can build limits together? Well, if I wanted to take the limit of something like this, what do I know about the constant term? If I take the limit of the constant piece, what am I going to get? Just that constant, right? And if I take the limit of the x term, what do I know about the limit of x? I just get to plug in, right? Okay, so do I get to just plug? So if I'm asking what is the limit as say x goes to, well, I've already used a for something, so let me use b. I claim that this is just equal to p of b. All you have to do is plug the number into the polynomial. Okay, but let's think about why that's true. Okay, what were the limit laws that we talked about last time? Okay, so when can you break up a limit and deal with each piece separately? What happens if you got a bunch of stuff added together? Can you just take the limit of each little piece and then add up all the answers? Provided that all of the individual answers actually make sense, right? Okay. Would they in the case of a polynomial? Yeah. Okay. So I can do this by saying, okay, what is the limit as x goes to b of a sub n x to the n plus the limit as x goes to b of a sub n minus 1 x to the n minus 1 plus dot 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 plus the limit as x goes to b of a sub 1 x plus the limit as x goes to b of a non. Okay, so our limit law, right, said that if we've got a sum or difference of things and each of the individual limits works out, we can just split it up and then add up all the answers. Okay, is that good? But what do we know about each of these individual things? So let's start actually from the right. What's this limit? A naught, because what is a naught? A constant. And if we approach anything of a constant, what do we get? That constant. Okay. Now, over here, what's the limit of, pretend that the A1 isn't there. What would the limit of, as x goes to b of x, it would just be b, right? Because x is going to be, right? If I've got an A1 out front, what do you think it's going to be? How about A1 times B? Yeah? Okay, so what we'd have is we'd have A naught over here, we'd have A1 times B here, and then what would the x squared term look like? It'd be A sub 2 times B squared, right? Does that make sense? No, Patrick? All right, well, let me write it out. Let me come over here. Limit as x goes to b of A sub 2 x squared. Okay, so that term is, I haven't explicitly written here. It's sort of hiding in the dot, dot, dots. Is that okay? Right, so I haven't explicitly listed it, but it's there. Well, if can I plug b into that? To A sub 2 x squared? Yeah, what do I get? A sub 2 b squared. Okay, any issues with doing that? Okay, and similarly, can I do it for all of the other rest of the stuff hidden in the dot, dot, dot with all these other bigger powers? Yeah, they all are going to work the same way, okay? And so what I get is A sub n b to the n plus A sub n minus 1 b to the n minus 1 plus dot, dot, dot plus that. Well, I don't know about you guys, but that's the same thing that we would get if we just plugged b into the polynomial in the first place. Okay, so what's the moral of the story? If you're taking in the limit of a polynomial, what do you get to do? Just plug it in. Okay. Now, there's maybe another reason or way that we could say why we're allowed to do that. Because what is true about the graphs of polynomials? Like, think about them. What properties do they have? Like, what's the sort of magic C word that we might use here? They're all continuous. Okay. And as we'll talk about in just a second, if you have a continuous function, you can take the limit by just plugging in. It's the discontinuous ones where you can't pull that trick. Okay. Now, we need to formally define what continuity means, and we'll do that. Okay. But for right this instant, take the word continuity to mean exactly what you think it means, and we'll put the technical crap to it later. Right. So, what did continuity mean to you in high school? Well, how did you know if a function was continuous? Arthur. Okay. Or what was another way to say the same thing? You could draw the graph without picking up your pencil, right? Which I was always sort of that contrarian, and I'm like, well, I can draw a function with the hole without picking up my pencil. I just do loop around the hole, and then off I go, right? And yeah, you were never told that. What, the picking up your pencil thing? Oh, well, that's good actually, because it's a reasonable, like, intuitive definition, right? It's not a technical reason, but it's good enough for, I guess, high school work. What were you told? There's no holes. Yeah, and it doesn't have those. Yeah. So okay. Yeah. So, but anyway, for right this instant, let's just take continuity to mean exactly what you think it is, and we'll put the technical mumbo jumbo on it later. Okay. So let's look at on the bottom of the first page here. The these limits. Okay. So what kinds of functions are continuous? Well, maybe a better way to answer that question would be what kinds of things could make functions be discontinuous? Okay, so this kind of gets back to Arthur's point. So what kind of things could cause problems? Holes, but how do we, like, when do holes occur? Yeah, okay. But like in terms of algebra, like the what kinds of things might cause holes or asymptotes or things like that? Divisions by zero, logarithms of negatives or zero, square roots of negatives, things along those lines, right? Yeah. Okay. Also, some of the trig functions get ornery if you start plugging in bad values. But like there are all of the basic, functions like x squared and e to the x and the log of x and so on. All of them, though, have the property that they are continuous on their domain. Okay, meaning, so what's the domain of a function? What's that mean? Yeah, the allowable input values for x. Okay, so are you allowed to take the square root of a negative? Not really, right? You get an imaginary quantity, but so maybe a better way to put this is, are negative values in the domain of the square root function? No. Okay, so it turns out that basically every function is continuous on its domain. So as long as the x value that you're approaching is in the domain of the function, you can just plug in. Okay, now let's look at the list of those 6 down there at the bottom. Which are the ones that we have to worry about? Or maybe better put, which one do we not have to worry about here? Which one of these limits is sort of like stupid easy? Yeah, the first one, right? Okay, because what's the domain of the function x plus 10? Are there any bad x's? No, we can just plug in. It's a polynomial even, right? We just talked about that. Okay, but what about the other 5 of these things? You might be looking at them saying, wait a minute, look at number 3, for example. I see some division happening there. But what's going to be the number x that causes problems for division on number 3? 2. Are we approaching 2? No, we're approaching 3. So, yeah, 2 is a problem, but fortunately, we don't need to care about it. We can just plug in, and that's the end of it. Okay, so what about the rest of these? Can we just plug in to all of them? Well, what else looks suspect to you guys? What's sus? You guys play, what is it? Among Us, that's it, yeah. Yeah, which one's sus? Which one are you going to throw out the airlock? Number 6. Okay, why are you going to really? You're going to throw number 6 out the airlock? Yeah. Okay. So, well, okay. So, are there any numbers that you're not allowed to plug into cosine? Nope. What about e to the something? Can you do that for any values? Yeah. Okay. So that was cool. But and number 4 looks like number 3 in a sense because there's division. But what about number 5 there? Square roots. What might be a problem? Square root of a negative. Are we going to get a square root of negative if we just plug in negative a half? Careful. Right. So because this isn't just square root of x, is it? So what would you be taking the square root of if you plug in negative a half? 1/4, which is fine. Right. So I tricked you. Gotcha. Yeah. Or bazinga. You guys watch Big Bang Theory? Or did you? I actually have a little like push button in my office that just says bazinga when you press it. I gotta put it right there, and that way every time I nail you guys, I can just bazinga. Yeah. No. I've also got a Staples Easy button. You guys may be a little bit too young for this, but they did a TV commercial campaign where they're like, Staples, that was easy. And they had like a button as a prop in the commercials. And they got flooded by so much like make the buttons that they actually started making them. And they were on the aisle of, the wall of temptation at the checkout aisle for like $5. And I'm like, well, I mean, I have to have an easy button. So anyway, okay, good. So yes, as long as the value is in the domain and the functions that you're dealing with are the usual suspects that you know and love, you can just plug in. The problem, of course, is that not always can you do that. Okay, so let's flip over to the other part. Okay, the next page. And a lot of these look very similar to the previous ones, right? But like, let's look at number 8 there. What's the problem here? Yeah, I can't plug in 7 because that's exactly what gives me a division by 0. So the tricks from the last page don't work. We're hosed. So we have to do something else. Okay. And this is sort of the interesting case. So let's take number 8 there. All right. Okay, so we've just established that I can't just plug it in. Okay, because if I did, I'd have a 0 in the bottom, and that's bad. Okay. Now, worse off, what would happen if I plugged 7 into the top? Oh, both of them are equal to 0. Well, that's even worse. So what do? Do we throw up our hands and say D and E and go back to bed? Or, huh? Yeah, we could factor it, right? So there's going to be a number of algebraic tricks that we're going to be able to throw at this thing that might work. Now, they're not necessarily always going to work, but they're things in our toolbox. Okay, so how does the numerator factor here? All right, so what was it? X minus 7 times x plus 4. Okay, so first off, do we all agree with that factorization? Yeah, and if you're ever unsure, just FOIL it back out and make sure you got what you started with, just as sort of a check. Okay, but what's so brilliant about the way that that numerator factored? Yeah, the x minus 7s cancel, and so now we're just taking the limit of x plus 4. Now can we just plug in? Yes. And in this case, we get 11. Okay, so essentially what's happening here is, and let's think about this, the function that we started with, that fraction, and the function x plus 4, are they identically equal for all values of x? No. Okay. Are they identically equal for any value other than 7? Yes. Yeah, if I graph them, they'd be right on top of each other. What's the difference, though, in their graphs? This one would have a hole at x equals 7. Whereas does this one, or sorry, just the x plus 4 part, does that have a hole anywhere? No. It's a straight line, no big deal. Okay, so what we have are two functions that agree everywhere except for one hole. Okay, so should their limits agree then? Yes. Okay, and that's what the theorem is that's stated here. Okay. Okay, so why did this work? It worked because the top factored in a way that we could cancel the problem and make it, disappear. This is kind of like when you don't want to finish your peas and you just kind of scoot them under the mashed potatoes, right? A little bit. We kind of made the problem disappear. Yeah, you kind of like peas. So it's weird because when I was really, really little, like 3 or under, my mother could just like I could eat nothing but peas and I'd be happy, right? Then I got older and I couldn't stand them. And then I got older still and now I'm sort of okay with them if they're made right. Um, but not if they're mushy or and actually mushy peas are a thing in England. Has anybody ever been to well, I guess they could do something crazy like that, but no, it's almost like just mashed potatoes, but made with peas instead of potatoes. And they like soak the peas in lye water overnight before they make it or something. And it's just, yeah, it was no. Yeah, it was. I mean, it's British cooking, right? Which is, yeah, actually, I saw a good meme that was floating around on Facebook yesterday that I sent to my dad, and it was essentially like British, like conquer the world for spices, also British, and then pictures of a bunch of British dishes. Like, we've conquered the world for all these spices, and then we still have this horrendous food. Yeah, yeah. Although I will say, when I was in England, the Indian food, oh my goodness, was it so good? Because there's Indian places like Indian food in the UK is kind of like Chinese food here in America, right? Like every little town has an Indian takeaway place, and that's what they call it, right? Takeaway, not to go. Um, yeah. So anyway, okay. So we basically have to be clever with our algebra. So let's talk a couple more examples here. Let's look at number 9. Oops. Because this one does factor, but you guys might not remember this factorization trick. Because the thing on the top is not x squared. If it were x squared minus 1, you guys would know exactly what to do. Unfortunately, it's not. Does anybody remember how x cubed minus 1 factors? I'll show you a trick. No, it's actually more complicated. Okay, you guys don't remember. That's okay. But once I show you this, you'll never forget. All right, so I'm going to change the question to x squared, or sorry, x cubed minus or plus y cubed. Okay, because we could have a plus in between. It turns out it's this. Okay, now you guys might think I'm insane here because I want to point out two symbols. This one and this one. What's the difference? Yeah, okay, but why? There's a technical reason for this. So the first one, plus or minus, you're very familiar with. You saw it every time you did a quadratic formula problem in high school, right? The other symbol you maybe didn't see as often, it's called minus plus. And it works the exact same way that plus minus does, except it's backwards from plus minus. So the reason we have these two symbols is if this one is a plus, that one is a minus. And if this one is a minus, that one is a plus. So it's always opposite of the other one. And that way we can encode sort of a pattern. Okay. Have you guys ever seen that before? No? Isn't that awesome though? Yeah. So it doesn't really matter which one you use if there's only one of those symbols. But if you've got multiple of them, this is how you tell, okay, when the plus minuses are plus, all the minus pluses are minus, right? So you can tell which ones are backwards from each other. Okay. All right. Now, you guys might look at this and say, how the heck would I ever remember that? But I learned this from some high school students. Soap. This sign is the same, or sorry, forgot this. It should be a plus minus. That sign is the same. The other sign is opposite, and the last sign is always positive. Soap. And that only works for cubes, though, so just keep that in mind. So this works for the sum or difference of two cubes. Okay, that's pretty cool. No? You guys don't seem convinced. Yeah. Yep. That's fine. Yeah. I mean, everybody's got to be a critic, right? Yes, always plus, always positive, whatever. But it's still soap, right? I became quite the connoisseur of soap in my youth. Palmolive had a nice olive taste, and you guys know what I'm quoting. Did anybody watch The Christmas Story for like 24 hours? Yeah, when he gets his mouth washed out with soap for saying the F word. So, have I ever been what? The museum, the house? Yeah, no, I haven't. I've always wanted to. In fact, that might be the one thing that could get my parents to come up and visit here during the winter, is that we could go on a family trip to the house, right? And see the leg lamp and yeah, yeah. So, okay. So applying what we just learned here, we've got the specific case where y is 1. And so ours is going to factor as x minus 1, same sign, opposite sign, always positive. Okay, you guys convinced? Yeah. Okay, so what fortunately happens here? Yeah, the x minus 1's cancel, and we're just taking the limit of x squared plus x plus 1, and that, what can we just do? Just plug it in, and what do we get in this case? 3. So that's all cool. Okay? Okay. So the last one I want to do is one like number 11 or number 12. Okay. Let me actually take number 12 because it's slightly more complicated. And then we'll go to the other ones later. Okay. So, and we're almost out of time, so we'll come back to this later. So we want to do this. Okay, so no factoring is going to save us, right? We're hosed in that department. Any brilliant ideas? Can't quite. We can't square it. I mean, if we did, we'd be changing the function is the problem, right? Which could therefore change the answer. But we can do something like, okay, so if we square it, we've changed the function, right? Could I multiply by something so that it looks like I changed the function, but I didn't really change the function? That seems like a trick question. So what I'm going to do is I'm going to multiply by something that's equal to 1, but doesn't look like it's equal to 1. Okay? And I'm going to be super sneaky here. Let me write it down. You guys would never in a million years think of this on your own. But once I write it, you'll be like, oh, of course. It's like the discovery of the Post-it note. Okay, where the hell did I come up with that? Yeah, having a PhD in math kind of helps. You've seen basically every problem under the sun. All right, but what did I do to the thing on the top, right? The square root is the whole irritation here, right? That we can't just magically make it disappear or factor or any stuff like that, right? And the other problem, of course, is the fact that we've got this division by 0 potential issue, right? But so I looked at that square root term and I said, okay, I'm going to multiply by that thing plus 2 instead of that thing minus 2. And then if I'm going to do it to the numerator, I have to do it to the denominator also, because otherwise I'm changing the function. Does anybody remember what that thing that I multiplied by is called relative to what we started with? It's called the conjugate of it. Yeah? Okay, why was this such a brilliant idea? And here's my rule of thumb. Whose conjugate did I use, the top or the bottom? Multiply out the top, but do not multiply out the bottom, because it'll make the next step easier. Okay, so the bottom I'm going to leave like this. Oops. Okay, multiply out the top. Well, I have to FOIL, right? So what's the square root term times the square root term? Just the stuff on the insides. The square roots cancel. Okay, but then with FOIL, I have to do the outer pair and the inner pair. And what are those both equal to? They add up to 0 because one of them is the negative of the other. And then I have to multiply the last terms and I get -4. So notice what happened to the square root. It kind of disappeared, okay? All right, now what's x plus 1 minus 4? Oh, would you look at that? Oops. Okay, so what can I do with the x minus 3's? Yep, just cancel those guys. And can I plug in now? Yes. From here to here? Okay, so I left the bottom alone, right? What's x plus 1 minus 4? X minus 3, right? Which is perfect because then, bam, right? Okay, so can I just plug 3 into this now? Yeah, sure. So up here, I have I have to FOIL, right? So I have to do first, outer, inner, last. So first would be the square root times the square root. That gets me x plus 1. Outer would get me the square root times 2. Inner would get me the square root times -2. Those are opposite, so they cancel. And then the last would be the -2 times the 2, which is -4. Yeah? Okay, can you just plug in now? Okay, and great. All right, we will continue with this on Friday.